Let me tell you about a problem in physics that has driven very brilliant people to consider some truly strange possibilities. Parallel universes where every possible outcome happens. Human consciousness creating reality. Mathematical worlds where particles don't actually exist until you look at them. These are not fringe ideas. These are mainstream attempts by serious physicists to solve a problem that has existed for 100 years and still has no answer. The problem is this: reality does not exist until you measure it, not as philosophy, not as metaphor, as experimental fact. A particle does not have a position until you measure where it is. It does not have momentum until you measure how fast it is moving. It does not have spin until you measure what direction it is spinning. Before you measure, the particle exists in something called superposition, all possibilities at once. Measure it, and the superposition collapses to one definite outcome. You see the particle in one place, moving at one speed, spinning in one direction. But here is the problem. Nothing in the equations of quantum mechanics describes this collapse. Nothing at all. The Schrödinger equation, the fundamental equation that governs quantum systems, is completely deterministic. You give me the wave function at one time, I can tell you exactly what it will be at any other time. The equation is continuous, smooth, reversible. Like Newton's laws or Maxwell's equations, you can run it forward or backward in time. No problem. Collapse is different. Collapse is sudden, discontinuous, irreversible. The wave function evolves smoothly according to Schrödinger's equation, evolving through superposition, and then when you measure, it suddenly jumps to one outcome. The equation does not describe this jump. The equation has no measurement in it, no observer, no collapse. We have an equation that predicts probabilities with absurd precision. Quantum electrodynamics matches experiments to 10 decimal places. Best theory in all of physics. But we do not know what the equation is saying about reality. We do not know when collapse happens. We do not know why collapse happens. We do not know what counts as a measurement. This is the measurement problem, and it is not solved. Now let me tell you about an experiment that makes this problem very clear. It is a thought experiment invented by Erwin Schrödinger in 1935. Very brilliant fellow, one of the founders of quantum mechanics. He invented this scenario not to explain quantum mechanics, but to show how absurd it becomes when you try to apply it to everyday objects. Here is what you do. You take a cat and you put it in a box. In the box you put a quantum device, maybe a radioactive atom that has a 50% chance of decaying in 1 hour. If the atom decays, it triggers a mechanism that releases poison. The cat dies. If the atom does not decay, nothing happens. The cat lives. You close the box and wait 1 hour. Now, here is the question. Is the cat alive or dead? You might say, well, either the atom decayed or it did not. Either the cat is alive or it is dead. I just do not know which until I open the box. But that is not what quantum mechanics says. Quantum mechanics says the atom is in superposition. It is both decayed and not decayed at the same time. Therefore, the device is both triggered and not triggered. Therefore, the poison is both released and not released. Therefore, the cat is both alive and dead. Not either alive or dead, you just don't know which. Both. Simultaneously. In superposition. Open the box and you see one outcome. Cat alive or cat dead. But when did the collapse happen? When you opened the box? When light from inside the box hit your retina? When the electrical signal reached your brain? When you became conscious of what you saw? Schrödinger invented this scenario to show the absurdity of applying quantum superposition to macroscopic objects. He thought it was ridiculous. Cats are not both alive and dead? Obviously. Except you see, we keep doing experiments with larger and larger systems, and quantum superposition keeps showing up. In 2011, researchers at the University of Vienna demonstrated quantum interference with molecules containing over 400 atoms. In 2017, a team at MIT created superposition in a mechanical oscillator you could see with your eyes. These are not single electrons. These are real physical objects. and they behave quantum mechanically. The boundary between the quantum world and the classical world, if there is a boundary at all, is blurry at best. So when does collapse happen? Where is the line? Now, there have been many attempts to answer this question. Let me tell you about the most important ones. The first answer, the one that dominated physics for 70 years, is called the Copenhagen Interpretation, named after Copenhagen, where Niels Bohr worked. Bohr and Werner Heisenberg argued that the quantum wave function is not real. It is just a mathematical tool for calculating probabilities. Reality exists only when measured. Before measurement, the question, where is the electron, is meaningless. It is like asking, what is north of the North Pole? A category error. The electron does not have a position until you measure it. Measurement creates reality. This interpretation works mathematically. The predictions are perfect, but it feels like surrender. It leaves the measurement process completely undefined. What counts as a measurement? Does it require a human observer, a detector, a single particle interaction? The Copenhagen interpretation does not answer. It just says, shut up and calculate, and for 70 years that worked, because the predictions were perfect. But it does not explain what is happening. It does not explain what measurement is. It does not explain why there is a collapse. It just says there is, and stop asking questions. You see, this bothered a lot of people. Einstein famously hated it. He said the moon is there even when nobody is looking at it. He spent decades trying to prove quantum mechanics was incomplete. He failed. But others took different approaches. If you take the mathematics of quantum mechanics seriously, if you do not add collapse by hand, you get some very strange possibilities. One possibility was proposed by Hugh Everett in 1957, a graduate student at Princeton. He said, what if there is no collapse? What if the wave function always evolves according to the Schrödinger equation, no exceptions, no special collapse process, just smooth, deterministic evolution? Then what happens when you measure a particle? Well, the measuring device becomes entangled with the particle. You become entangled with the measuring device. The wave function of the entire system, U plus device plus particle, goes into superposition. In one branch of the wave function, you measure spin up. In another branch, you measure spin down. Both outcomes happen. The universe splits. You just experience one branch. Another version of you experiences the other branch. This is the many worlds interpretation. Every quantum measurement splits the universe into branches. All possible outcomes happen. You just see one. Your other selves see the others. Think about that. This interpretation preserves determinism. It eliminates collapse completely. The Schrödinger equation always holds, no exceptions. But it multiplies universes without limit. Every quantum event, every interaction, every measurement splits reality. There are versions of you reading this who made different choices 5 minutes ago, versions where you do not exist, versions where quantum randomness played out differently and the dinosaurs never went extinct. Many physicists take this seriously. It is not fringe. In a 2011 poll of physicists at a conference on quantum foundations, many worlds tied with Copenhagen as the most popular interpretation. These are serious people considering this seriously. But it has a problem. Why do you only experience one branch? Why does probability feel real if all outcomes happen? These questions have answers within the framework, but they require careful thinking about what probability means. Now, there is another interpretation that takes a completely different approach, proposed by David Bohm in 1952. He said, what if particles always have definite positions? What if there is no superposition of position at all? In Bohm's pilot wave theory, every particle has a real position at all times. Always. It is guided by a quantum wave, the pilot wave. The wave evolves according to Schrödinger's equation. The particle follows the wave. When you measure the particle, you find it wherever it happens to be. The wave determines the probability distribution, but the particle is always somewhere definite. This theory reproduces all the predictions of quantum mechanics exactly. Every experiment, every result. But it requires something strange. The pilot wave must be non-local. It must allow instantaneous influences across space. affect one entangled particle, and the pilot wave instantly changes the trajectory of its partner, no matter how far away. Einstein called this spooky action at a distance. He thought it was absurd. But experiments have proven it happens. Alain Aspect, John Clauser, and Anton Zeilinger won the Nobel Prize in 2022 for proving quantum entanglement is real and non-local. Einstein was wrong about that. So pilot wave theory works. It gives particles definite positions. It eliminates measurement as a special process. But it trades superposition for non-locality. You choose which strangeness you prefer. There is yet another approach. In 1986, Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber proposed modifying the Schrödinger equation itself. Add spontaneous random collapses, very rare for single particles, maybe once every 100 million years, but frequent for large systems because they have many particles. This is the GRW theory. It explains why microscopic systems show quantum behavior and macroscopic systems do not. A single electron stays in superposition because spontaneous collapse almost never happens. A cat has 10 to the 26 particles. Collapse happens almost instantly. The cat is never in superposition. Problem solved. But you have to modify the fundamental equation of quantum mechanics. You have to add a random collapse process that nobody has ever detected. And you have to choose parameters, numbers like the collapse rate and the collapse width, that are not predicted by the theory. You tune them to match observations. Some physicists like this, others think it is inelegant. But here is the important thing. It makes different predictions than standard quantum mechanics. For very special, very carefully prepared systems, you could test whether spontaneous collapse happens. Experiments are being done right now. Now, let me tell you about some of these experiments. Because this is not just philosophy, this is real physics that people are testing. In 2023, researchers at ETH Zurich created quantum superpositions of mechanical oscillators containing trillions of atoms. Trillions. These are macroscopic objects. You could see them with your eyes, and they behave quantum mechanically. They ring like bells, and you can put the ringing itself into superposition. The bell is both ringing and not ringing. Other experiments test whether gravity causes collapse, an idea proposed by Roger Penrose. Maybe when a system becomes massive enough, space-time curvature becomes ambiguous in superposition, and this ambiguity causes collapse. Experiments with masses in superposition in orbit, where gravity is weaker, could test this. The experiments are being planned. There are also experiments with photons that create Schrödinger's cat scenarios at the quantum level, single photons in superposition of different paths interacting with detectors in clever ways. These experiments test where the quantum to classical transition happens. So far, no spontaneous collapse. Superposition persists. Quantum computers depend on this. They maintain superposition in systems with dozens or hundreds of qubits. Each qubit is a quantum two-level system. 50 qubits in superposition represent 2 to the 50 states simultaneously, more states than there are atoms in U. If collapse happens spontaneously, quantum computers would not work, but they do. Superposition persists as long as you isolate the system from the environment. And here is something interesting. When the environment interacts with the quantum system, superposition seems to disappear. This process is called decoherence. Discovered in the 1980s, the quantum system becomes entangled with the environment. The environment has so many degrees of freedom that you cannot track them all. Superposition is still there, mathematically, but it is invisible, spread across the environment. You cannot see it anymore. Many physicists thought decoherence solved the measurement problem. It explains why you do not see superposition in everyday life. The environment destroys it too quickly. But decoherence is not collapse, it is entanglement spreading. The wave function still contains all possibilities. They are just invisible because they are entangled with the environment. You still have not explained definite outcomes. You have just explained why superposition is hard to see. The measurement problem remains. Think about what this means. We have a theory that is the most successful theory in the history of physics. It predicts the magnetic moment of the electron to 11 decimal places. It describes everything from why the sun shines to why your computer works. It is the foundation of chemistry, of molecular biology, of materials science. Every piece of modern technology depends on quantum mechanics being correct, and we do not know what the theory says about reality. Does reality exist before you measure it? Do particles have properties or only potentials? Does consciousness play a role in creating reality? Are there parallel universes branching every instant? Does gravity cause collapse? Is there a pilot wave guiding every particle? Do spontaneous collapses happen? Nobody knows. Different interpretations give the same experimental predictions but tell radically different stories. In Copenhagen, reality is created by measurement. In many worlds, all realities exist. In pilot wave theory, one reality exists and particles always have positions. In GRW, reality collapses spontaneously. These are not small differences. These are different pictures of what existence means. You see, Richard Feynman said, "I think I can safely say that nobody understands quantum mechanics." This is what he meant. We can calculate anything. The predictions are perfect, but we cannot explain what we are calculating. We do not know what the wave function is. We do not know what measurement is. We do not know what happens during the one thing we actually observe, the one thing that is not described by the equation. Some physicists think this is fine. Shut up and calculate. The predictions work. What more do you want? Others think this is a crisis. The central process of quantum mechanics, the process that connects theory to observation, is not explained by the theory. That seems like a problem. And experiments keep pushing the boundaries. Quantum superposition in larger and larger systems, tests of collapse models, tests of the role of gravity, tests of decoherence. We are looking for where, if anywhere, the quantum world becomes the classical world, where superposition stops and definite outcomes begin. So far, we have not found a boundary. Superposition persists in systems far larger than anyone expected 50 years ago. Maybe there is no boundary. Maybe the world is quantum all the way up, and classical reality is an illusion created by decoherence. Or maybe there is a boundary, and we just have not reached it yet. The measurement problem is the open wound at the center of physics. 100 years after the discovery of quantum mechanics, we still do not know what happens when you make a measurement. We do not know what reality is like before measurement. We do not know if there is a definite outcome or all outcomes. We do not know if the universe splits or collapses or neither. We have the most precise, most successful scientific theory ever created, and we do not understand it. Some people find this disturbing. How can we use a theory we do not understand? How can we trust it? But I think there is something beautiful about it. We have learned to calculate what nature does with extraordinary precision. We can predict experiments, build technologies, describe phenomena across 30 orders of magnitude in energy, all without knowing what reality is. That is how science works sometimes. You find patterns. You find mathematics that describes the patterns. The mathematics makes predictions. The predictions are tested. They work. You keep going. Understanding comes later. Or maybe it does not come at all. Maybe the universe is not obligated to make sense to creatures like us, creatures whose brains evolved to throw rocks and find food, not to understand quantum superposition. But we keep trying. We keep doing experiments. We keep proposing new ideas, new interpretations, new tests, because this is how physics is. You discover something that works, and then you find something you cannot explain, and you keep looking. Nobody knows what measurement is. Nobody knows when collapse happens. Nobody knows if reality exists before you look. But we keep looking. That is science, and I think that is beautiful.